All right, sweet. So we are recording. And you guys wanted to do practice problems, so let's start there. So okay, here we go. So 34 and 44. These are out of order, but okay. So 34, and before we do that, someone asked, I wasn't at SI today. Was it just 18? So yeah, we just continued with chapter 18 today. Part of the session wasn't recorded, so I will redo it for you guys and post it for you, but that'll just probably be tomorrow, not today. Alrighty. So for the people who weren't here today or don't remember or want to review, so racimization is essentially when we do a tautomerization, but we have something like this that has a chiral center. So when we're doing the tautomerization, I'm just going to do the simple version of the reaction. So going forwards, we go from the ketone to the enol, but we can also move backwards again from the enol back to the ketone. And when we do that, we are actually going to make two different products. So since we started with a chiral center, we went to something planar. Now when the hydrogen attacks here again in order to reform sp3, I'm just going to move this ever so slightly, we can actually make the R and S products. And the reason for this is we could either add from the top face or from the bottom face, which just means it could either add, there's not enough room here, it could either add wedged or it could add dashed. So someone who was at SI or has done this reaction before, why could we get either of these products? Exactly, because we have something planar that we're working with, and if it's planar, it has no preference for whether the hydrogen will add wedged or dashed. Therefore, you will get a 50-50 mix, which we like to call what? What kind of mixture? Yes, so we call this a racemic mix. So that's the basic, that's the basis of racimization. So then the question asks you, which of the following would undergo racimization in base? So the main thing you have to focus on is would undergo and racimization. So from this diagram here, what do you guys think is required in order to do a racimization? A chiral center, cool. So this first one has two benzene rings. Can we have a chiral center here? Nope. All right, now these three all have wedges and dashes, but one of them we can kick out immediately because it does not have multiple unique groups. Which one do you guys think that is? Number 4, exactly, because all of these are exactly the same, so that cannot be chiral. All right, so now we know that both of these are chiral, so can both of these be our answer? No. Okay, why not? You're correct, but why not? I'll zoom out so you can see the reaction as well. What do we need besides chirality in order to go from this to this? An alpha what? An alpha hydrogen, exactly. So you need a chiral alpha hydrogen, and in one of these cases, we are missing that. So which one of these is missing the alpha hydrogen? Number 2, exactly. So we have 3 carbon groups, no hydrogens. So our answer is going to be C. And I will zoom out if you guys want a screenshot or whatever. Any questions, or does this make sense? Make sense? Okay, cool. So I'm just going to scroll up a teeny tiny bit just to see if there's any other ones we can come back to. Okay, cool. So we're going to go back up and practice a couple more of those, but first let's do number 44 because you guys asked for it. So, first of all, before we do this reaction, can someone who was either at SI or has seen this before tell me what kind of reaction we will be doing? What's the name? Halogenation, perfect. And how did you know that? Don't look at the answer. Yes, exactly. So Cl2 means that we have a halogenation. It could also be Br2 or any other halogen, but usually we either have chlorine or bromine. So when we have a halogenation, step 1 is going to be find our alpha carbons and figure out which one we're going to use. So we have alpha 1, alpha 2. Which one is the best option in order to do the enolate chemistry? Alpha 2, cool, and why is that? Because they're both secondary. They both have 2 carbons, right? So why is alpha 2 better than alpha 1? You're on the right track, but it's even more obvious if you just take like a look. I'll give you a second, and then if you guys need a hint, I'll be more than happy to give you one. So you said it's more acidic, and that's a good way to look at things when you're choosing between the 2 alpha groups, but there's something even more simple. Someone said because of sterics. No double bond. Okay, so what do you mean by no double bond? You guys are on the right track, but you're missing something super, super simple. You're thinking too much into it. Alpha 1 has a double bond. Exactly. So is there a hydrogen here? No. There's only a hydrogen here. I told you guys, you were thinking way too deep into it. Alpha 1 is not even an option because there is no hydrogens there. People get mixed up with that all the time. So please make sure that the alpha carbon that you pick has a hydrogen present. People do that all the time. But you guys have the right intuition. Okay. So we are going to use the base, and we're going to steal that hydrogen. So I'm just going to redraw our OH so we don't have super weird arrows going around. Steal that, give the electrons back. Sure, that's a benzene ring. All right, so now that we have a negative charge here, what can happen? Yeah, you know what? Tell me first what could happen. You can add a chlorine, but while that's true, let's put some vocab words in there. So how are we going to add chlorine? The chlorine is going to attack, the C minus, which is just the carbanion, is going to attack the chlorine. Sorry, I don't know how to speak apparently. And these electrons are going to go to the chlorine. And so this carbon right here acts as a what? Or acted, I should say. As a nucleophile. Awesome. So this enolate carbon is the nucleophile. And this is the electrophile. So once we attack, we add a chlorine. And ta-da, we did one substitution and we added a chlorine, right? But to my people that were here today, do you guys remember what is the rule when you have a halogenation in base? It repeats the reaction. Cool. And so just for the sake of not leaving anyone out, I'll just open this up and show you guys. So on the left side, we have our reaction mechanisms when we have a halogen with base and with acid. And this special case, but we're not going to talk about this one right now. So usually, if we have a halogenation happening in base, we're going to be able to repeat the reaction multiple times in order to fully substitute the most favorable alpha carbon. So I can say that one more time. When we have a halogenation happening in base, we will be able to do the reaction multiple times in order to fully substitute the most stable alpha carbon. So that is the rule, but why does that rule not really matter in this case? It's already fully substituted because we only had one hydrogen present. Perfect. So I'm going to close this side. We did the whole reaction, so we know that this is going to be our correct answer, so you guys can just match it. But let's say, and then someone said, can I repeat that? So yes, before I move on, which part did you want me to repeat? Like the whole base rule for halogenation? Yes, okay. So basically, we know that we can repeat the reaction in order to fully substitute the most stable alpha carbon. But in this case, it is already fully substituted because we only had one hydrogen present. So when we do the reaction one time, it becomes fully substituted. We have no more hydrogens to steal. Good. So yes, if we have a halogenation in base and we have multiple hydrogens, we are going to do the reaction as many times as we can in order to replace all of the hydrogens that are on the most favorable alpha carbon. So if we had, if this methyl was instead another hydrogen, we would add 2 chlorines. Cool. All right. So now with that, you guys can kind of see which one would be the answer. But let's say on the exam you space out or you forget something or you're like, oh, I don't remember exactly what would happen. Let's try to see how we could go through this and get rid of some answer choices. So the first one I would immediately get rid of is this dude, because why did this become an electrophilic aromatic substitution? Right? If we have another carbonyl somewhere, we're never going to choose EAS when we've already learned about enolate chemistry. That's gross. We don't want that. The next one I would get rid of is this guy, because, or I won't. What happened to our carbonyl? Like, what? How did this happen? I hate that answer. Ew, go away. And then we have this guy and this guy, which, first of all, why would we add an OH? That's weird. OH is just going to be a catalyst, and we know that because Cl2 means halogenation. So this doesn't make any sense. So now, if you're stuck between 1 and 2, I understand. Why could we automatically kick out number 1, though? What's wrong with it? It's not an alpha position, exactly. So this is alpha, this is beta, and then just for funsies, that would be gamma, so on and so forth. So this added to the beta position. We don't want that. So our correct answer is B. And then someone said, I haven't seen chapter 18 yet, but this made sense. Good. Any questions so far? Right? Like, sometimes you can just look at it and you're like, yeah, some of these just don't make any sense. Like, some of these look better than others. And then, yes, we can absolutely do this. Do number 47, excuse me. So I'm going to scroll. And it is the same exact thing, but in acid. So before I go ahead and say anything to you guys, tell me the difference, please, between an acid catalyst and a base catalyst when we're doing a halogenation. I'll go ahead and open this up for you. Yes, so the acid catalyst does not repeat the reaction. And the reason for this is, in order for the acid to repeat again, let me make this a little bit bigger. In order for the acid to repeat again, you would have to protonate the carbonyl and then eventually work our way to taking away this hydrogen. And that's not preferable because this bromine is pulling all the electron density down. And so now these lone pairs don't want to go and get protonated because they're already being pulled away by this bromine. They don't want to go ahead and steal a hydrogen. That would be a waste. But up here, we're able to do this so easily and so readily because we already have base in solution. And the base can just go ahead and steal that hydrogen all in one step. We don't need all these little baby steps to prepare to steal the hydrogen. For that reason, halogenation will only be done multiple times in base. In acid, it's only ever going to happen one time. I know I went through that kind of fast. Any questions? I can repeat anything if you guys want. Make sense? Okay, sweet. So I'm going to close this setup. So in this example, we have one hydrogen again. So if we have H3O+, I'm going to redraw it just so there isn't weird arrows. What would be the first step? What is pretty much always the first step if we have an acid catalyst? Protonate. And what is the point of protonating, please? What does it do? It makes the electrophile more electrophilic. Perfect. So far we haven't really done anything. The hydrogen is still here. All we did was make this positive. And so now in solution, sorry, I keep zooming in and out. I'm trying to find a good balance. We have Cl2 and we have H2O. And so our whole goal is to take away this hydrogen. So what could we use as a base to take this hydrogen? What do you guys think? So you guys said chlorine. And while we can do chlorine, the way I like to usually draw out this reaction is to use H2O. Because as we've learned before, drew too many lone pairs. We know that water can act as an acid or a base. So in this case, it will go ahead and act like a base to steal this hydrogen and give that electron, give those electrons here. And so we get a negative charge. Whew, finally. Okay, so at this point, what are we going to do? Attack, exactly. So we're going to attack here, give those electrons back. Sorry, that's just too much. I can't. We attach a chlorine. And now we have to take care of this plus charge. So now what do we have in solution that can go ahead and deprotonate that guy? Cl minus. So that's why I like to go about the mechanism this way, just so I have that nice Cl minus to deprotonate at the end. I don't know why it went from blue to red, but whatever. So we ended up making actually the same product. So which one of our answers are we going to pick? Number 2, exactly. So B is our answer yet again. So now you guys can kind of see how to do the reaction 2 different ways, but get the same answer. Any questions? 84, well, let's look at it. This we haven't gone over in SI yet, so I do not expect you to know it. So yeah, I don't expect you to know it yet, but since you guys are here and since you asked, you are pretty much looking for the least sterically hindered alkyl halide for the Malonic Ester reaction. So you would go ahead and pick the one that has the least stuff going on, and in this case, it would be A. Without knowing any context, I know it's kind of hard to make sense of, but you can just remember until we go over it. Malonic ester synthesis just wants the least sterically hindered alkyl halide. So for that reason, we'd pick A. So at this point, we can either, because there's a couple other really great questions for chapter 18 that we can go over, we can either do that, or we can keep doing mechanisms, or we can go back to something else. What do you guys want to do? Okay, so we got 1 vote for more practice problems. Okay, so it seems like most people want that. And yes, I can go ahead and repeat this one. So we haven't done the Malonic Ester reaction, but you guys can just remember that Malonic Ester wants the least steric hindrance. So we would want the alkyl halide that's like the smallest or the least sterically hindered. And so out of these options, we know that A is the least sterically hindered. Good? Okay, cool. So let's go back up. Let me see where chapter 18 starts. Cool. Okay, so don't look at the answer. Which of these is the ketone enol tautomeric pair? Okay, cool. So one person said 2, one person said they guessed and got 2, which you're right. But let's go over it just so you know for sure and you're confident and it's not a guess. So I was going to leave it, but it was too ugly. I couldn't deal. Okay. So we know that for a tautomeric pair, let's just say we have an OH, we're going to steal one of the alpha hydrogens and we're essentially going to move it to the alcohol. So steal that. This will go up here and this will go up here. And this is going to be the shortest version of the mechanism. So we have O minus, we made a double bond, and we're missing our hydrogen. And in the next step, we just protonate and we get this. So essentially, the ketone enol tautomeric pair is always going to go from whatever this R group is, to something that looks like this. So we're always going to have a double bond to an alpha carbon, and we're going to change the ketone to an alcohol. And the only one of these that actually even has a double bond is this one, and this one. Number 1 and number 3 don't even have double bonds, so we get rid of that. And then between 2, 4, and 5, this double bond and this double bond are much too far away, so 2 is the only one that makes sense. And then someone said, so you're pretty much just moving the hydrogen up. Yeah, we can kind of think about it. So we're just plucking this hydrogen and attaching it up here. And in order to do that, we just have to rearrange our double bond. So you can think of our double bond moving 1 down and our hydrogen moving 1 up. Make sense-ish? Any questions with this one? So let's go on to the next one. Did this one. Did this one. So let's do this one. Okay. So before you even do any kind of chemistry, which one of these is absolutely ridiculous and can be gotten rid of? Two and three are pretty silly and we can get rid of them because they are not in the alpha position. So alpha, beta, gamma. So that's out. We also know that I don't know why I said it like that. We also know that this bromine is on the gamma position, so we can get rid of that. What about 4 and 5? Why are those ones absolutely so silly? I love my hair. Because there's not even a carbonyl. Exactly. This one's gross because it's just 2 bromines and no carbonyl, so what the heck is that about? And then this one has an OH and a bromine. Why did they get rid of the carbonyl? Who knows? Goodbye. So our only possible answer is A. And then, just to do a concept review, why didn't we add 2 bromines? Why did we just add 1? We know we still have a hydrogen here. Because it's an acid, true. And we would only do multiple substitutions if it was a base. And someone said, this is way too easy. Will he actually give us questions like this? Yeah. Usually, the reason I think this class was so much easier than Orgo 1 was because a lot of the times, at least half the questions will be kind of let's say easy, but kind of easy to pick apart the wrong answer from the right answer. So even if you didn't really know anything about how this chapter works and all you knew is that you add a bromine somewhere, you could get rid of these 2 and then you have a better shot. So yeah, test taking skills is really huge for this class. He definitely will ask you questions like this. I got distracted playing with my the sticker on my water bottle, so I kind of lost my train of thought. Any other questions with this one? Okay, cool. So let's move on. We haven't done this reaction yet, so let's skip it for now. We can skip that for now. Okay, so that's all the practice problems in this handout or in this packet that we have learned the mechanisms for. So what would you guys like to do now? Bless you. We have 12 minutes. And yes, we can definitely go ahead with the reactions. Is everyone cool with that? Where am I? Alrighty, so no one else said anything, so I'm assuming they're all okay with it. The next reaction is going to be the Hels-Volhard-Zelinsky reaction, and I'm never going to say that again. And so this reaction, besides being a mouthful, is actually not that bad. So, first things first, what do we immediately recognize from these reagents? BR2 and PBr3. Okay, so which one does what? Since we just did BR2, yes, PBr3 is a protecting group, and someone also said that it's going to turn the carboxylic acid into an acid halide. You're both absolutely correct. So we know that PBr3 turns OH to Br. And so what does the Br2 do? What kind of reaction? Nucleophilic attack, yeah, we can kind of call it that, but even more specific, I guess, to just the Br2. What did we just talk about? Starts with an H. Halogenation, perfect. And while nucleophilic attack is technically correct, the only reason I was a little hesitant about that is because we learned about a couple different nucleophilic attacks, so I just wanted to make sure you guys knew the most specific answer for this case. So, as you guys said, first things first, we're going to go ahead and turn this into an alkyl halide. So we went from OH to Br, or I'll make that red so it matches. And then we also have Br2, which we said will do a halogenation. And it's important for you guys to note that we made something in solution. What did we make? Or I guess what did we create as a byproduct? A racemic mix? No. Okay, I don't know if this was meant to be funny, but someone said we made, and then like an empty space, and I thought that was so funny. Come on, guys, what happened when we got rid of this? What's it floating around as? OH minus, exactly. So now we have some base in our solution, so I'm going to write that down. And we have Br2. So, and see, I don't even have to be here anymore. You guys just said in the chat the OH minus is going to steal an alpha hydrogen. Exactly correct. So these electrons steal that hydrogen, give those electrons back. And so now we have a negative charge. And so that negative charge is going to act like what? A nucleophile, sweet. So it's going to attack what exactly? The bromine. Doesn't matter which bromine because they're exactly the same. And so now we have made, sorry. Why can't I make anything attach? There we go. So now we have one bromine on the carbonyl, and we attached one bromine here. And someone said chapter 18 reminds me of the other chapters. I am so happy to hear that, because that means that you have been paying attention and now you're making connections and you're realizing that this is all the same stuff over and over and over again. And I am so happy to hear that. And I'm being 100% genuine. I know I sound sarcastic, but I'm not. Sorry, I just got much too excited. I'm going to calm down. So, what do we think at this point? Are we good? Do you guys want to do anything else? What do you say? Do the next one. So do you mean like the next reaction? Do you think this is our final product? Good. You are right. So this is our final product. And yes, I'll go through this really quick to give you guys a summary. I'm just going to move it over a tad bit because it's driving me crazy. So basically, what we did is we had this carboxylic acid. We used PBr3 to replace the OH and make it into an acid halide. And then we used our base to steal this hydrogen and create the enolate, which is this guy. And and then this negative charge was able to steal this hydrogen. Was able to steal this bromine. And in the end, we created this lovely product. And no, it doesn't have a specific name that you have to know. The only thing I want to know is if we had a base catalyst in solution, how come we don't do this again? Why don't we replace the other hydrogen? So it's not just a halogenation. Someone asked, is this only a halogenation? It's like a spicy halogenation. So first you had to create your acid halide, and then you did the halogenation. So yes, it is stable the way it is, but the reason we're not going to react again is because we only had 1 mole of this base. This wasn't our catalyst to begin with. So it wasn't here. We just made 1 mole of it. That's why we can't react again. So make sure for the Volhard-Zelinsky reaction, you're not going to do it multiple times, even though it looks like there's base. It's just going to happen 1 time. So for this next one, we have almost the same exact reaction, but now we have H2O added to the mix. And so I'm going to go ahead and copy this and paste it right here because the first 3 steps are going to be exactly the same. So the first step we use PBr3 and replace the OH with the bromine. And then we do our enolate chemistry. We form the enolate. We make the nucleophile. The nucleophile attacks, and we add it to the alpha position. Sorry, I don't know why my stutter is so bad. So we add a bromine to the alpha position, and we have this bromine right here. The only thing left in solution is now H2O, and that is the new step. So we have H2O in our reaction. And what do you guys think we could possibly do with H2O? We could protonate. Cool. So what are we going to protonate? The carbonyl. That's a pretty solid plan. We seem to do that a lot. So we go bam, bam. And so we make now we have a plus here. And we have a nice colorful molecule. And we have now OH minus. So what now? What can we do? we could take away the hydrogen, but then we would just be going backwards, right? We could take the alpha hydrogen, but there's something more favorable here. I want you guys to think back to chapter 17.
Are we going to attack the
just think about it for a second.
carbon?
So we have a protonated carbonyl. We have an OH minus. So put yourself back into chapter 17. What could we do at this point? What would Rosemary do?
The Rosemary method. I don't know.
We could do a proton transfer, but where would we put the proton? You know what? Better question. So anything with a negative charge is a what or a what? Nucleophile or a base. Perfect. So if it acts like a base, we would just go backwards in the reaction. So it has to act like a nucleophile. And you guys actually got it at the last second there. I just didn't get a chance to see it. So you guys said we're going to attack the carbonyl carbon. And specifically, one person said the oxygen is going to attack. Perfect. So if the oxygen is going to attack, we know that we could do the long version of the reaction, but what would the short version? What would the short version be? Essentially, the nucleophile will attack, and what will happen to the bromine? It'll be the leaving group. Cool. So I'm essentially just going to do this for short. And so we get still have a plus here, but that's okay. We'll take care of that. We replaced our bromine with an OH. And now we have Br minus, so what are we going to do? Deprotonate. Perfect. So Br minus is going to steal that hydrogen, give those electrons back, and finally, we get, oh my gosh, ta-da! We get our final product. Yay! Someone asked, is there a Rosemary method? Absolutely. So all I want you guys to remember is in the first one, we have PBr3 OH to Br, halogenation, Br2 halogenation. So we add a bromine to the alpha position, and H2O is just going to mean Br back to OH. So we know that if we have Br2 and PBr3, we end up with a bromine on our carbonyl carbon and a bromine on the alpha carbon. If we have H2O present, we are going to keep everything the same and just add a bromine at the alpha position. Does that version make sense? The kind of simplified version? So someone asked for the exam, will the H be there? Do you mean like in the final product, this one? It probably won't be drawn. I just like to put it there to remind you guys that it's not going to be like two substitutions. You will still end up with one hydrogen, but that hydrogen is still implicit, so it probably won't be drawn. Make sense? Does this kind of answer your question? Cool. Awesome. So that is it. I hope this was helpful. I hope you guys learned something. You guys have any questions, comments, concerns? Are these all the reactions for chapter 17 or chapter 18? We have two more. Well, we have technically three more, but these two are exactly the same reaction. They just have two different names. But we essentially have two more left. And then I can zoom out if you guys want to see these. I know it's kind of like you feel defeated because you still have so much left. But those two reactions are pretty much exactly the same as what we've been doing. So hopefully it won't be too bad. I think you guys have been doing great so far, so it won't be like anything too crazy. Even though I know this one looks really scary, but gotta love the rosemary method. Any other questions, comments, concerns? If not, I will stop the recording.